Okay, welcome to Chapter 6 on confidence intervals, and this is for Lesson 2. So we've already done Lesson 1, confidence intervals for the mean, so we'll be using a lot of that information. If you need to, you can look back at those notes. Today we're going to do confidence intervals for the mean, where our population mean is unknown. Okay, so we're going to learn here how to interpret the t-distribution and use a t-distribution table, and also how to construct and interpret confidence intervals for a population mean when our population standard deviation is not known. Remember, that's what our omega stands for. Okay, the t-distribution. When the sample size is less than 30, and the random variable x is approximately normally distributed, it follows a t-distribution. Okay, so here's the formula that you see in your notes. Okay, we can also rewrite this formula to look like this, where we're doing our t times the sample over the square root of n equals our mean minus our population mean. Okay, our critical values of t are denoted by t sub c. Okay, properties of the t-distribution. The t-distribution is bell-shaped and symmetric about the mean. The t-distribution is a family of curves, each determined by a parameter called the degrees of freedom. The degrees of freedom are the number of free choices left after a sample statistic such as x bar is calculated. When you use a t-distribution to estimate a population mean, the degrees of freedom are equal to one less than the sample size. Okay, so you'll see that when we want to find the degrees of freedom, oftentimes they'll abbreviate that to df, you just take your sample size minus 1. Remember, the total area under our t curve is 1 or 100%, just like a normal distribution. Okay, the mean, median, and mode of the t-distribution are all equal to 0. So oftentimes you'll see 0 right in the center. Okay, so like right here we can see in the center right there is 0. So as the degrees of freedom increase, the t-distribution approaches the normal distribution. So after 30 df, the t-distribution is very close to the standard normal z distribution. So you can see here, the orange is when you have df degrees of freedom of 2. And so notice how there's a big gap here and it doesn't quite reach the height. If we increase that to 5, it gets a little closer. And then obviously when it is greater than 30, okay, then we get more like a normal distribution there, where the ends get very, very close to the edge there, and in the middle it's a little bit taller. So notice the tails in the t-distribution are thicker than those in a standard normal distribution. So they're talking about here and here. They get a little closer to the normal as we increase that number. Okay, on example 1, we're going to find the critical values of t. So find the critical value of t sub c for a 95% confidence when the sample size is 5. Okay, so remember using our standard distribution, 95% looked like this. Okay, but now with these, when we go to find the area under there, okay, we want to put back this tail right there. So when we go to find the area, we're going to take, and we're thinking about just subtracting that 0.5, because notice that's what's left. If I do my 1 minus my 0.95, that's how I'm getting that 0.05. But then I have to divide it by 2 because there's 2 areas right there. And so if I divide that piece by 2, okay, that's where I'm getting the the 0.025 for this little area here. Okay, and when I go and I add that onto my 0.95, that's where this number is coming from. This is just another way to show how to find it, is they're just taking this first to get that 0.05 divided by 2. And so we get the area to be the 0.975. So if you were plugging this in on the graphing calculator, you have to find that number first. But we can go to our second vars. Okay, remember that takes us to distribution. This time we're going to take number 4, inverse of t. We've got to plug in our area. And then to find our degrees of freedom, we're going to take our sample size is 5. So like they show you up here, 5 minus 1 gives you 4. So we would be plugging in this 0.975 and 4 in there in order to get that these numbers here. Okay, you're going to get the 2.776. And remember, you can have the negative one of that or the positive one. So that's giving us, those are our limits there on either side. So 95% of the area under the t-distribution curve with 4 degrees of freedom lies between negative 2.776 and positive 2.776. And again, we got those numbers by plugging in on our graphing calculator. Okay, the confidence intervals for the population mean. So a C confidence interval for the population mean, if we look at this one, we have this equation. So we got x bar minus E is less than our mean is less than x bar plus E. So basically we're taking that, we're just subtracting the E on one side, adding the E on the other side. And again, this is how we are finding that E. So the probability that the confidence interval contains our mean is going to be C. Okay, so let's go through and look at what this looks like for each of these pieces. So first thing, we're going to identify the sample statistics. So remember, your N is your number in the sample. Your X bar is your mean of the sample. And remember, your S is your sample standard deviation. Okay, so this is how we're going to find X bar. We're going to add all of our numbers together and divide by how many. And then to find our standard deviation, remember we did this whole long complicated process to find that. A lot of times they'll just tell us what it is. Okay, then we're going to identify the degrees of freedom. And again, that's just taking the number in your sample minus 1. And then to find the confidence C and the critical values, we're going to use our inverse T. Okay, find the margin of error. So again, we're going to plug our numbers in here to find the margin of error. And then remember, to find our right and left endpoints, we're just going to take X bar minus E, X bar plus E. So again, that's just taking the mean. And then writing it as our confidence interval. So let's look at this now. In a random sample of 20 customers at a local fast food restaurant, the mean waiting time to order is 95 seconds and the standard deviation is 21 seconds. Assume the wait times are normally distributed and construct a 90% confidence interval for the mean wait time of all customers. Okay, so first of all, let's write down what we do know. Okay, we were given the standard deviation. Okay, we know what our mean time is, the 95 seconds. We know our sample is 20. So finding each of our important statistics here. Our N is 20. It gave us the mean to be 95, gave us our standard deviation of 21. and we're trying to do a confidence interval of 90%. So to find our DF, which remember is our degrees of freedom, that's just our n minus 1, so 20 minus 1 gives us 19. If we want to find our area, remember we are going to take, to find the area, we're going to take and we're going to think about if you have 9.90, okay, then we have to think about doing 1 minus, well, what's left? If I take that away from 1, I get 0.10. If I divide that by 2, okay, 1 minus that is going to give us our 0.05. Sorry. Give us our answer. We're going to get, yeah, our 0.05. So that's what's on each side. So now if I take that and I take my 0.90 plus my 0.05, that's going to sum up to my 0.95. So that's the area that we're looking for. Okay, we already have our DF that was calculated right here, so we're going to plug that in to be 19. And again, on the graphing calculator, to get the inverse of t, remember you're going to go to your second vars and then choose number 4. Okay, if you do that, then that is going to give us this number for TC. Okay, and that comes up to be our plus or minus our 1.729. Okay, so that's what we're going to have on either side. Okay, then to find our error, we're just going to plug in each of those numbers. So we're going to have our 1.729 times our S was our 21 over our N, which was our 20. If we plug that into the calculator and just round it to 1 decimal place, we get about 8.1. Okay, so that's our margin of error. So now if we go back to our mean, which again our mean was the 95 seconds, okay, if we take that and we're just going to go through and do our mean minus the 8.1, which gives us our 86.9, and we're going to do our 95 plus our 8.1, and that's going to give us our 103.1. Okay, and so those are the two numbers that you want to write there in our blanks. So let me get rid of this part right here. So we did that. So you can see there that we are 90% confident that the mean wait time for all customers is going to be between our 86.9 and our 103.1 seconds. Okay, if you are trying to decide whether to use normal distribution or t-distribution, you can come here and look at this chart. So, first question to ask yourselves, is your n greater than or equal to 30? If it is greater than or equal to 30, then you can use the normal distribution. If your population mean is unknown, then just use your sample mean instead. So in place of our omega, you would use S. If it is not greater than 30, then you have to ask yourselves, is the population normally or approximately normally distributed? Okay? If the answer is no, you cannot use the normal distribution or the t-distribution. So this is if it tells you it's skewed at all, then we can't use either one. If it is normally distributed or approximately, and we know the population mean, then we can use the normal distribution. So again, we would plug in, okay, our population mean, and then use this formula to find our error. If you don't know the population mean, then use this instead. And to find our degrees of freedom, make sure that you do the n-1. So those are the examples that we just looked at where we were using a sample. And so yes, it was normally distributed. We didn't know the population mean, so we used the sample, and we used n-1 for our degrees of freedom. So let's look at some examples, and we have to decide which one to use. Okay, so this says determine whether to use the normal distribution, the t-distribution, or neither. So here our n is 50, the distribution is skewed, S is 2.5. Okay, well, it says our sample size is 50, which is greater than 30. So if you look back at your chart, okay, it says as long as it's greater than 30, we can use the normal distribution. So even though this says it's skewed, because our sample size is greater than 30, we can use the normal distribution. For part B, our n is equal to 25, the distribution is skewed, and S equals 52.9. Well, this one, if you look at the first box, it is not greater than 30, so we have to go down because it says no, and then it asks, is it normal? Okay, it is not normally distributed, so in this case, neither distribution would be used. The sample size is less than 30, and it's skewed, so neither one can be used. For part C, it says that our n is equal to 25. The distribution this time is normal, and we know the population mean to be 4.12. So it doesn't fit the first category. It's not greater than 30, but it is normally distributed, and we do know the population mean. So this would be going down 2 and then over 1 as far as the chart goes. So this would be case C there. Okay, we can use the normal distribution. Even though it's less than 30, okay, it's normally distributed, and we do know the population standard deviation. So we can use that. So this is the end of this lesson, so go ahead and get your Chromebooks and start working on the homework on Math Excel for 6-2, confidence intervals for the mean.